So we continue with our refraction of lenses, refraction through lenses. We are starting with the third part of the chapter, that is sign convention and lens formula. So this part of the chapter helps you to identify that if you place a particular object in front of a convex lens or a concave lens, so if I know that what is the distance between the lens and the object, then I can easily calculate what will be the distance from the lens to the image, what will be the size of the image if I know the size of the object, and accordingly I can also find out, if I know both this, I can also find out the focal length of that particular lens. So with this, they are basically numerical based things by which you can calculate the either the distance of the object from, sorry, distance of the image from the lens, or the focal length of the lens, or the image of the height of the image so formed of the object. So this is what we are going to learn in this part of the chapter. So sign convention or measurement of distances is we follow the Cartesian sign convention to measure the distance in a lens, according to which the optical center of the lens is chosen as the origin of the coordinate system. So what we see over here is, if I consider that this is the x-axis and this is the y-axis, then the origin over here, this is also the optical center of the lens. So this O is optical center. We know that these are positive, these are negative, these are positive, and these are negative. Okay, so that is as per the coordinate system of graph. We know that the right side is positive, left side is negative, upside is positive, lower side is negative. O is the origin, which is also the optical center of the lens. So when you take the optical center of the lens as the point O, then we can find out this. Similarly, we can also have the same thing done even for the concave kind of a lens. So this is a concave lens. So this is a concave lens here. This is again the x-axis, this is the y-axis, this is negative, downwards, this is positive, upwards, and to the right is positive, to the left is negative. Okay, so this is the origin, and this origin over here is the optical center. So now we always consider that the incident light will be from this side. So this is the incident ray. Okay, the direction of the incident ray will always be this way. So this is the direction of the incident ray. So if there is a direction of the incident ray, that means the object is placed somewhere here. Okay, what we see? Okay, let me read out and then we can discuss this further. Yeah, the optical center of the lens is chosen as the origin of the coordinate system. See, optical center. The object is considered to be placed on the principal axis to the left of the lens. So to the left of the lens is the incident ray. So the object is placed to the left of the lens. That means if the object is placed over here, or we place it over here, we see that this is the distance between the object and the lens. This we call it as U. Okay, so we have it over here as U is distance between object and lens. Okay. The next thing is V is distance between image and lens. F is focal length of lens. Okay, the next is O is height of object. I is height of image, and M is magnification. So these are the different terms which we'll be using in this particular part. Okay, we'll be using these as the terms in the required things. So these are the terms which we will be requiring over here. So first thing is, all the distances are measured along the principal axis from the optical center of the lens. The distance of an object from the lens is denoted by U, the distance of the image by V, and the distance of the second focal length, that is focus, is F. So focal length is the distance between the second focal length. Now you can see the second focal length over here will be over here. This will be F2. Over here, this is going to be F2. We very well know that in case of a convex lens, the F2 is on the other side, and in a concave lens, F2 is on this side over here. So this is F2 in this case and F2 in this case over. So you can see F over here will be positive. Over here, F will be negative. So let's see one by one. U, so this is convex, concave. We get over here U always negative, F always positive. Okay, U will always be negative, whereas F will always be positive in case of convex. Here what will happen? Here it will be U is always negative, but F is always negative. F is over here, which will be negative. Clear? Right. Now what we see is the distance measured in the direction of the incident ray are taken positive, while the distance opposite to the direction of incident ray is called as negative. So any distance which I am taking on this side are taken as positive, on this side are negative. That's very simple. You can take it from the origin itself. Anything which is lying over here in the positive axis will be positive, and the negative axis will be negative. The length above the principal axis is taken positive, while the length below the principal axis is taken negative. So this part is taken positive, this part is taken negative. This is positive side, this is negative side. Same over here also. So figure shows the distance of convex and concave lens according to the sign conventions. By sign convention, the focal length is equals to OF2 of the convex lens is positive, that of the concave lens is negative. The distance of object U is in front of the lens is always negative. The distance of image V is positive if the real image formed behind the lens, while it is negative if the virtual image formed in front of the lens. So here we see in this case, we know that we had drawn the ray diagram last time, so we know that if it is a real image, the image will be over here on this side. Okay, यहाँ पे सब जगह पे image होगा. And if it is a virtual image, it will be on this side, a bigger one here or here, wherever it is. So it will be on this side. So we know that V is equals to positive for real and V is equals to negative for virtual. Okay. Whereas we already know that for a concave lens, always the image will be over here dotted ऐसे करके मिलने वाला है. So it will always be negative. So V is also negative. So in this, because every time it is virtual only, because it is virtual, that is the reason it will always be given as negative. So we see that in case of a concave lens, U, F and V will always be negative. All these three values will always be negative. There can never be a positive value of U, V and F in case of a concave kind of a lens. In case of a convex lens, U and F, U is always negative, F is always positive. V will be positive for real images. For all real images, it will be positive. It will be negative for the image which is formed by virtual. Virtual image will always be negative. Okay, that is the sign convention for convex and concave. And then comes the lens formula. So the lens formula is given as this is the lens formula, 1 upon V minus 1 upon U is equals to 1 upon F. This is the lens formula. Okay, this is 1 upon V minus 1 upon U is equals to 1 upon F. It's the same thing for here also. It's the same thing. 1 upon V minus 1 upon U is equals to 1 upon F. This is the same throughout, whether it is this way. But so, when you are taking these values over here, you are going to use the sign convention before you apply the values of U and V in the formula. So, that's why it gives you that the equation. So, the equation relating the distance of U, distance of image V and the focal length F of the lens is called as the lens formula. It is same for both the convex and concave lenses and is given by 1 upon V minus 1 upon U is equals to 1 upon F. The derivation which is given over here in the textbook is not in your scope, so you need not worry about it. Derivation is not included in the syllabus. It is just there for the understanding, but it is not required to understand also. I would say better skip it completely because it is not required. So now we see for, okay. So note, in numericals, the known values are substituted with their proper signs and then the unknown quantity is obtained from its with both proper signs. According to sign conventions, for convex lens, U is always negative, F is always positive, V is positive for real image, V is negative for virtual image. But for concave lens, U, V and F all are negative and the numerical value of U is always greater than V. Okay, numerical value of U is always greater than V. So here it is that U is always greater than V. Only in case of concave. Now we come to the next part, and that is linear magnification. Linear magnification is the ratio of the length of the image to the length of the object. So it is not sufficient to know the position of the image of an object by a lens, but it is also required to know its size. We cannot just say, okay, image mera yahan pe hone wala, that's okay, that's more than sufficient for me. No, it is not sufficient because I need to know whether the image will be formed, will be a magnified image or a diminished image. So that information about the magnification is also required about the particular kind of a image. So when the position of the object changes, there is a change in the position as well as the size of the image. That we already seen that whenever there is a change in the position of the image, the object, the position of the image also changes, and accordingly even the size of the image changes. The ratio of the length of the image I perpendicular to the principal axis to the length of the object O is called as the linear magnification. So the ratio, so we have got over here magnification, M magnification is equals to, we are given the length of the object, that is I upon O. Okay, it will be I upon O, where I is the height of the image and O is the height of the object. So length of the image or length of the object, height of the image, height of the image, one and the same thing. So we see that the ratio of I upon perpendicular I and O is called as the linear magnification. It is generally denoted by the letter M and is related to the distance of image to the distance of U for both the convex and concave. Though this is also equal to, we can say, V upon U. Okay, so this is another important formula over here, that M, that is magnification, so it's small m, sorry. The magnification is equals to I upon O or is equals to V upon U. This is V upon U also gives you the same ratio of magnification as compared to the I upon O. So that's why we see over here that is denoted, it is generally denoted by letter small m and is related to the distance of image V and the distance of object U for both convex and concave lens as linear magnification, as M is equals to length of the image I upon length of the object O is equals to V upon U. So derivation not required again, so you can skip the derivation of this part also. So that's why we are not taking the derivation of any of these things. So finally, note, for a linear image, for a real image which is inverted, magnification is negative. So here important thing is that for a real image, M is negative. For virtual image, M is positive. You can see in case of a real image, you know that U is negative, V is positive, so automatically this overall will be negative. For virtual image, both are negative. You can see both are negative, so negative, negative become positive. So we will always find that the magnification value, if it is negative, it means it's a real image, and if it is positive, it is a virtual image. So the sign convention, we are going to use this V and U with the sign convention. So according to sign convention, you always V over here. If it is a virtual image, will be negative, and if it is U will be negative also. So negative, negative become positive. So it's a virtual image. Here, if V is positive for a real image, so V positive and U is negative, so it will be negative. So we will always know that real images will always have a magnification which will be negative, whereas the virtual image will have magnification which is positive. For a real image which is inverted, the magnification M is negative, while the virtual image, the magnification M is positive. You can also note it one more way, because you know that the image which is real will be formed in the negative axis. You can see below, so it will be negative side. That's why real images, the magnification will be negative, whereas the virtual image will be erect, which will always be on the top, so it's positive. This is another way of remembering this thing. Thus, a convex lens can have a value M positive as well as negative, but a concave lens always has the value of M positive. The numerical value of M is greater than 1 if the image is magnified. So if M ka value is greater than 1, we don't consider the sign at that time. When we say it is minus 3, means it is 3. It is 3 times, so it is magnified. But if I say it as 0.3, then it is diminished. So your value of M, okay, the absolute value of M, that means without the signs, whatever is the value, that is the numerical value of M, whatever is there, will indicate whether there is a magnification or diminished by kind of an image. If the value is 1 or greater than 1, then it is a magnified image. If it is less than 1, it is a diminished image. So the numerical value of M is greater than 1 if the image is magnified, and 1 is for the image which is of the same size of the object, and is less than 1 for diminished images. Thus the numerical value of M is always less than 1 for concave lenses. We always know it is going to give you a diminished image, so it will always be less than 1 in concave lenses, while it will be greater than or equal to or less than 1 for convex lenses, depending upon the position of the object. So depending upon where the object is being placed, you are going to have different values of the point of the magnification. The next what we are having is the power of a lens. So when a beam of light passes through a lens, it gets diverted from its path. The deviation produced by the lens is expressed in terms of its power. The lens which produces more deviation has more power. Thus, a deviation of the incident ray produced by a lens, okay, the deviation, the change in the direction of the pathway. So deviation produced by the of the incident ray produced by a lens on refraction through it is measure of the power. A thick lens, that is a lens having a surface area more curved, thick lens, is of a shorter wavelength. See, because if it is thick over here, that means the radius of curvature is very small, इसीलिए ये curvature ज़्यादा है. Thin होगा तो इतना ही है, तो यानी क्या सर्कल इतना बड़ा हुआ. See, when it is like this, the circle is so big. When it is like this, the circle is only so small. So you can see that, and you know what is the focal length over there? Focal length is half of the center of curvature, half of the radius of curvature. So अगर ये इतना बड़ा है, तो इतना बड़ा circle है, तो उसका क्या हुआ? The radius is less. Okay, so focal length, radius is more, so the focal length is also more, right? So we see that a thicker lens is of a shorter wavelength, focal length, and it deviates the rays more. So more the thicker, more will be its deviation. While a thin lens, a lens having surface of less curvature is of larger focal length and it deviates the rays less. Hence, power of lens expressed in terms of reciprocal of its focal length. Its units are is diopter. It is diopter, and power of a lens is 1 upon focal length. So, ठीक है ये सब ठीक है. I'll erase everything. So we have over here the power of the lens power is equals to 1 upon focal length in meters. Okay, 1 upon focal length, which is in meters. And it is given by the sign D, that is diopter. Okay, diopter is the unit of the power of lens. While giving prescription to a patient, an optician does not quote the focal length of the lens, but he quotes the power of the lens. A lens is of power 1 diopter or 1D if its focal length is 1 meter, that is 100 centimeters. So if it's giving you at 1 diopter, then it is focal length is 100 centimeters. Depending on the direction in which the lens deviates, the light ray, its power is either positive or negative. If a lens deviates a ray towards its center, that is a converging type, center, the power is positive, and if deviates away from the center, the power is negative. Therefore, power of a convex lens is positive and the power of concave lens is negative. Okay, convex lens, positive power because they are converging time. It is going towards the center, so positive. If it is going away from the center, negative. So, okay, that will be negative for concave. Thus, power of a convex lens of focal length 20 centimeter is 5D. While the concave lens of the same focal length is minus 5D. If two thin lenses are placed in contact, the combination has a power equal to the algebraic sum of the powers of the individual lenses. If a convex lens of power plus 2D is kept in contact with concave lens of power minus 2D, the combination will have zero power and it will behave like a glass plate. So, if one lens is like this, other lens is concave and convex together, one of 2 plus 2, other of minus 2, when you mix them together, it becomes just like a glass slab. So, that is how it is going to add up. So, they always add up. The power of the lens add up. So, if I am having two lenses, one of 1 and another of 1 also, then I am having something of 2 diopter. So, that was about the basic things about the chapter. So we'll just write down all the different formulas which are coming up over here so that we are having the complete details of these things when we start with the numericals of this particular chapter. So we'll first of all write down the formula part. So first one is U is distance of object from lens. To V is distance of image from lens. 3. F is focal length of lens. Fourth point will be I or is length of image. 5 is O, which is length of object. 6 is M, which is magnification. And 7th is P, which is power in diopter. Okay, so these are the main things. Now we come to the sign convention. So we have our sign convention. Convex, U always negative, F always positive, V positive for virtual image, and negative for real image. Okay, then comes concave. U always negative, F always negative, V always negative. Clear? So after this, what we have is the lens formula. So 1 upon V minus 1 upon U is equals to 1 upon F is the lens formula. Based on this, the next thing is, so this is the first formula. The next formula is M, magnification, is equals to I upon O is equals to V upon U. Okay, here M positive for virtual image and is negative for real image. Okay. Secondly, if M, absolute value of M equal to 1, same size. If M is greater than 1, magnified. If M is less than 1, it is diminished. Okay. The next what we have is power P in diopter is equals to 1 upon F in meters. In power, convex, positive, concave, negative. So in a way, I can say that this is the summary of this particular chapter. You learn this by heart, automatically numericals will be very easy. These are the terms U, V, F, I, O, M and P. Convex, U negative, F positive, V positive for virtual, negative for real. Concave, U negative, F negative, V negative. Formula 1 upon V minus 1 upon U equal to 1 upon F. M is equals to I upon O or V upon U. M will be positive for virtual image, negative for real image. Absolute value of M is equal to 1 and is the same size. M is greater than 1, magnified image. M is less than 1, diminished image. Power of the lens in diopter is 1 upon F in meters. Convex lens always power will be positive. Concave lens always power will be negative. Is it clear? So this was about the sign convention. In the next video, we'll move with the numericals of this particular chapter.